The NASA IV&V program formed an independent test capability team with the purpose to acquire, develop, and integrate spacecraft simulators to allow the dynamic analysis of mission-critical software systems for NASA. The simulation environments that we have developed in-house are the Global Precipitation Measurement Project and also the James Webb Space Telescope. Some of the key challenges that we face as an independent organization is that we're independently managed and really have a separate organizational structure from the development projects that we work with. To mitigate these challenges, what we've done is we've relied on software simulation to allow us to simulate the hardware components of a system so we can bring those in-house, simulate the pieces without acquiring them, and develop systems that our engineers and analysts can use to test and exercise flight software systems.
NOS is the NASA Operational Simulator, which is a generic architecture for developing simulations here by the ITC team. What we do is it encompasses hardware models and our own custom middleware that we developed. The hardware models are reusable and reused across several missions such as GPM and JWST. The middleware is responsible for ensuring that all of the components of the simulations communicate with one another. It is a reusable architecture. We plan on reusing it in the future. It's developed in-house here at the IV&V facility.
Our hardware modeling approach is based on recreating what the hardware would actually do. So we get the software, hardware, ICDs or interface control documents, or what other supporting documentation we would need, and we create models that actually implement that behavior. We model the hardware so that we can run the flight software without the hardware, and that allows the flight software to execute in an environment where it believes it's actually executing in flight on the hardware, but it's actually on our laptop or wherever we want to run it.
We've developed an automation framework to run these end-to-end system tests autonomously and multiple times in a row. We've done this because some of these tests take hours and hours to run. So what we've done is taken that entire system, we will run them through the ground station, through Simics, to the flight software, and through all the dynamic simulators to eliminate that entire overhead of man time. We can add more and more tests to these, and they'll continue to be put into our suite and run over and over again with almost no additional work from the user.
Typically, this IV&V program has done static analysis where we look at requirements and code, and do tracing and things of that nature. But a few years ago, we decided that we needed to focus on dynamic analysis, where we execute the flight software in its native environment. So the only way we can do that is by doing simulations. So we've created simulations where we can execute the unmodified flight binaries. So what that allows us to do is inject faults and do all kinds of really nice things to ensure that the software does what it's supposed to do before it goes to flight. The ITC team deploys our simulators in the lab using virtualization technologies. So we're able to deploy any of our sims, no matter the operating system or platform, on any workstation or server using newer virtualization technologies. We can deploy to the cloud and virtually anywhere and access it from anywhere in the world.
Running a project, you really worry about the other two aspects of it, and that's cost and schedule. And that's probably where the tool has the greatest value. The cost factor on the spacecrafts are immense. Everything has to be 100% working. Everything on GPM, which is a Global Precipitation Measurement Satellite, is dual fault tolerant. It means any fault can happen on the spacecraft and it will not cause the spacecraft to fail. As part of this, it becomes a very, very expensive vehicle to fly, in the neighborhood of a little under $1 billion. It's the largest spacecraft ever being integrated at NASA Goddard Space Flight Center. So it's very, very important to make sure we don't waste time. It's one of the most important things that the project's concerned with all the time, because we want to keep things rolling, keep things moving towards our launch date. The cost per month is in the tens of millions of dollars per month. So a day slip costs a whole bunch of money. During the development, we actually found one failure that we weren't able to recreate any other way. And we used Simics to actually bring up the system and regenerate the error, and we were able to find the fault and fix the fault. It's something that never actually manifested itself in the actual spacecraft, but it manifested itself in a test case, and it was a flight code that was running on the spacecraft. So it was successful, and there was a lot of positive reinforcement given back by the project.
This has made our life easier, and it's also added an additional level of rigor to our work. Basically gives us the opportunity to find empirical evidence that we can provide to the development projects. We are here to ensure that the NASA software systems are of the utmost quality.